Sons, you two have followed me for some time already. But your punches and kicks are still not fast and powerful enough. To practice Kung Fu, it isn't enough just to learn the techniques. You must also learn about force and motion. And now, it's time for me to teach you some basic scientific concept. Look! Do you think they're fast? But can you tell who is the fastest?
How can we tell? Their movements look different and they start at different time. The distance they have moved are different too.
That's right. If we want to find out which object is moving the fastest, we often put them together and compare them as if they are running races. We try to see who needs the least time to cover the same distance. But if we don't have a race, we can still compare who moves the furthest within the same period of time.
The distance and time they each moved are different. How can we compare them?
If we know how much time it takes an object to travel a certain distance, then we can work out the distance that it travels per second or per minute. And this is called the average speed. The one with the greatest average speed is the fastest.
Average speed? I've heard of speed before, but why link it with average?
Speed is the distance that is traveled by an object in a unit of time. It is easy to work it out. We just need to divide the distance by time. The SI unit of speed is meter per second. We may also use kilometer per hour as the unit in our daily life.
However, very often, an object moves faster or slower at different times during the journey. If we need only a rough idea of the speed and not the changes in between, we can simply divide the total distance by the total time. This is the average speed.
I see. If a horse runs for 40 kilometers in 30 minutes, the average speed is 40 times 1,000 divided by 30 and then 60. That's 22.2 meters per second, right?
How can we work out the speed of Bruce Lee's fist and that of a chameleon's tongue when it is catching a prey?
Someone tried playing Bruce Lee's film in slow motion to work this out, and it is based on the distance moved by his fist during the time. Wow! It's around 30 meters per second. It is even faster than a running horse. Then, is his punch faster than a tongue of a chameleon?
There is a lot of research about that on the web. Go and search the answer for me.
What took you two so long? You both were fast when you first started. I've been enjoying my cup of tea already.
Master, because you know Qing Gong. Of course you can get here in no time. We were filled with strength when we started, and we even ran. But we ran out of breath after a while. So we started to walk for some time before we ran again. But we never stopped.
Not me. I jogged the whole time. Actually, Master, why are we coming to this faraway place? Are we here to learn something?
So you two took the same amount of time to cover the same distance, but with very different speeds in the process. That's what I want you to know. Often, for long-distance sports such as running or traveling by car, the speed varies along the way. The same speed is rarely maintained from the beginning to the end. You two are typical examples. If I just divide the total distance by total time, the average speed that I get cannot reflect your changes in speed during the process.
So, we are here to do some research on long-distance sports.
Look over there. With our naked eyes, it is hard to see the changes in speed of the train in different phases. But if we know the distances it travels at every interval, for example, every second, we can plot a distance time graph which gives a clear idea of how its speed changes during the journey.
It is moving so fast. How can we record it?
There is no way to see it with our naked eyes, but we can shoot a video and use a software to mark the places of the train every 5 seconds. We can then work out the distance that it travels every 5 seconds. I've already plotted it to save some time. Take a look.
This is interesting!
This is a distance time graph. Look at the x-axis here. It shows the change in time, while the y-axis shows the distance it has traveled. The line actually consists of many points. A point on it represents the distance that the train has traveled at a particular time.
Let me see. The line is slightly curved at the beginning.
However, it becomes a slanting straight line in the middle for a long period of time.
The next part after that is slightly curved again, and then it becomes flat.
What did the motion of the train look like to you just then?
When it started, it moved faster and faster until at a certain point, it began to travel at a constant speed. I see. There are two totally different phases. When it was speeding up, the line was curved. When it traveled at a constant speed, the line became a slanting straight line.
What happened to the last two parts then?
It slowed it down as it was approaching the station and finally stopped. I see. The line also became curved when it slowed down.
The train stopped after it reached the station. The distance didn't change anymore, and so the line was flat then.
Good. You two learned pretty fast. The health management app that I recommended to you the other day does not only record your daily exercises, it also gives graphical representations of your daily exercises. Now, take your phones out and open your distance time graphs.
Okay, here it is.
So what does a graph tell you about your motion?
Didn't you say you didn't stop? What do these fill parts mean?
Oh no! The app is really awesome!
Oh no! It is a distance time graph that is really awesome, as you said. Now, let me ask you, how far had you two traveled after 20 minutes while I was having my cup of tea?
Master, We have been talking for so long. Shall we order something to eat?
Good idea.
Excuse me.
Yes, sir, yes, sir.
A steamer of char siu bun, a steamer of siu mai, and a pot of jasmine tea,
Oh,
please.
okay.
Master, I see now that objects are either at rest, moving steadily, speeding up, or slowing down. This is not complicated at all.
That's not all. But we can classify various motion into uniform motion and non-uniform motion. The speed isn't changed when an object is at rest and moving at constant speed. We call this uniform motion. For objects that is speeding up or slowing down, the speed is changing. We call this non-uniform motion.
These motions can easily be recognized in a distance time graph.
char siu buns.
Wow, this waiter is a kung fu master. He delivered the char siu buns with one arm. Let's eat now.
What did you see besides the char siu buns? Can you see how the steamer moved?
Though we don't have its distance time graph, we can still see a little bit of it. When he pushed at the steamer moved quickly and slid forward a little bit. It then stopped it slowly.
Try using the term that I taught you.
It started to move in non-uniform motion. Then it was in uniform motion, and in non-uniform motion again.
Is that so? Can you tell which is uniform motion and which is non-uniform motion?
Master, what does the motion of an object have anything to do with us practicing kung fu?
You have to learn more about force. A lot of forces are in action around us. Even though we cannot see forces, we can see their effects and say that there are forces acting on something. For example, when I pick up this water bucket, it will leave the ground. Or when two kids play badminton, the shuttlecock will fly around in the air. However, these are just the different effects of forces that are acting on the objects.
Master, what do you mean by the different effects of forces?
In this world, things are not as simple as they look. Look at this thing in my hand. What is its state of motion?
It is at rest.
And why is that?
Come on, you're holding it.
Oh my!
Relax. It's just a water bottle. Look, I was telling you that things are not as simple as they look. All I did was releasing my hand. So why did it fall?
Because of gravity?
Right. Everything on Earth is constantly being pulled towards the center of the Earth. If there isn't an upward force acting on it, everything will just fall towards the ground.
Because everything on Earth is being constantly pulled towards the center of the Earth. things that we hold in our hand will fall when we release them.
Look at it this way. When I was holding the water bottle, though it was at rest, it was actually under the influence of the force of gravity and the friction between it and my hand. While the Earth's gravity pulled the water bottle down, the friction between my hand and the water bottle pulled it up and prevented it from falling. The forces were balanced. Therefore, it was at rest.
It was at rest because the forces were balanced. I got it now. An object will stay at rest when the forces acting on it are balanced.
Not really. Have you tried skydiving?
No.
Let's go now.
How does it feel?
Wow, it is really thrilling. I'm not asking about this. I'm asking whether you can feel the changes in your speed. Before the parachute was open, I thought I was falling faster and faster, and I could even feel the skin on my face loosen up. After the parachute was open, the falling slowed down a lot, and it is stable and comfortable now.
And do you know why? Let's discuss this after we land.
Oh, Master, I have filmed you. Let's look at the films.
Really? So, how would you describe our motion?
You were falling faster and faster. My camera almost couldn't follow you. After opening the parachute, your speed became stable and you landed slowly.
You experienced it yourself, and you watched it from another angle. But you both discovered the same thing. Do you know why?
Master, you're telling me not to look only at the surface again. I was pulled down by the Earth's gravity. That's why I fell.
You weren't just falling. You were falling faster and faster. I see. That means an object will move in non-uniform motion when there is a force acting on it.
Strictly speaking, when an object is moving in the air, there is a force opposing its motion. The force is called air resistance. The air resistance between you and the air was opposing your falling. And this was why you felt like the skin of your face was loose.
However, if the air resistance isn't as large as the Earth's gravity, they can't be balanced. That's why we fell faster and faster.
That means objects move in non-uniform motion when the forces acting on it are not balanced.
Correct. Then what about the part after the parachute was opened?
After the parachute was opened, I felt the parachute blocked a lot of air, and the speed suddenly decreased a lot. It was stable and comfortable.
Opening the parachute greatly increased the upward air resistance. This balanced the force of gravity that was pulling you down. That's why you felt in uniform motion.
Do you understand now?
Yes, when all forces are balanced, the object will be at rest or moving in uniform motion. I got it now.
Okay, it is for you.
No, I'm full. You can have it.
Eat more, bro.
Master, please take this.
I'm not hungry. You two have it.
Oh, you have it first.
You're skinny, bro.
Oh, you're skinnier than me.
I will have it. Why? I mean, why did the steamer of siumai move like this?
Because we pushed it.
Are you trying to tell us not to look at things on the surface again? It was so confusing just then. I don't know what to say.
If you cannot explain it, why don't you draw it?
Draw it?
Actually, to explain or predict the motion of an object, we can draw a free body diagram to show all the forces acting on it and see if they are balanced.
Free body diagram? What's that?
As the name implies, the free body diagram ignores the surroundings and considers only the object and the forces acting on it. In a free body diagram, we use labeled arrows of different lengths and directions to show all the forces acting on the object. Take the steamer of siumai as an example. Negate the vertical force and assume there wasn't any friction between the table and the steamer. Let's draw the steamer first. It doesn't need to be detailed. We can use a simple figure to represent it, like this. Then we can add arrows to represent the forces acting on the steamer.
Well, I pushed the steamer to him, like this. The steamer went to his side.
It doesn't work like this. The tail of the arrow should touch the object at the point where the force is applied, like this.
Then I pushed it to him, like this. The steamer was at his side.
We pushed it together after that. The two forces were the same, but in opposite direction. They were balanced. Therefore, the steamer remained at rest there.
Then you pulled the steamer. As there wasn't any other force to balance it, the steamer moved towards you in a non-uniform motion, right?
Good. What if there was friction between the table and the steamer, and that the force I applied was the same as the friction, but in opposite direction when the steamer was moving towards me? How would you describe the motion of the steamer?
The steamer would move towards you in uniform motion.
Ha ha ha! Now that we're getting to grips with analyzing force and motion, we can see things that can't be seen by the naked eye.
Don't be ridiculous. You have only started to learn how to tell whether the forces acting on an object are balanced or not. It isn't as simple as that. You still have a lot to learn.
So, Master, when will we practice Kung Fu again?